realistic decisions.
Real quick, how's it doing? You go to a coffee house and someone was online banking to get into they're still pretty tough to.
No, it's in this class. If you wanted to go steal somebody else's online banking, you're going to do it in this class. Let me point it out. Yeah, if you want to steal somebody's password in a coffee shop, I was just doing it at a conference I was at. All you do is this thing right here, SSL strip, Project 21. Project 21, you can steal everybody's password out of a coffee shop if they're using Wi-Fi that's unencrypted. And now that's the big news this week is somebody cracked WPA2. So when that comes out next month, you'll be able to do it even if the wireless is encrypted. And it really works. In fact, I used it. I gave a talk last weekend, and just before the talk, I had to wait a half hour, so I tried it, and I got a PayPal passwords this way, and I got Equifax passwords this way. So most people are still vulnerable to this attack, and it's 10 years old. Moxie Marlinspike figured it out and told us all about it in 2008, but people still have not updated their crap. This is the amazing thing about security. It's like medicine. You know you shouldn't smoke, shouldn't drink, you should get some exercise. People just don't do it. In the same spirit, they know a bunch of things not to do in security, and they just do it anyway. So, you know, that's, yeah.
Use a vulnerable browser?
No, what happens is they don't use HTTPS all the way.
For PayPal? So
yes, for PayPal does not use HTTPS all the way. They use a redirect to get to HTTPS, and the redirect is not secure. So I can grab it before it's secure, and it doesn't notice that it fails to ever become secure. It's awesome. Almost every website is vulnerable to this. When you get to the project, you'll see I have a whole list of them there to try. I did. Microsoft was vulnerable for 2 years, and it's only like 3 months ago they finally patched it. So I had to switch to like Salesforce and stuff. But an incredible number of people are vulnerable to this attack, and even because their management doesn't understand and their staff doesn't understand. They tell them to update to HTTPS, but their old page is on HTTP, so they just put a redirect to move from that to the new site, and they call it the job done and leave it that way forever. But that doesn't do the job at all because the redirect is over HTTP. And that's just like having a building and getting big locks and locking all the door and leaving the back door just hanging open. It's amazingly pointless, but all the people from the bottom to the top of these companies don't understand security. So they feel like it's worth spending their money locking every door except one, and that'll be fine.
So in Project 21, you say use Firefox, is that for a reason?
What's that?
In Project 21, you say use Firefox.
Oh, yeah, I think, yeah, because Chrome has some defenses against this that Google keeps putting in. Yeah, it works so, it's actually pretty difficult to do on Chrome because Google finally got fed up with this, and they started patching their browser. So, and now it's getting to the point where most browsers will warn you when you're putting stuff that looks confidential into a non-secure page. And Firefox even warns you now. It doesn't stop you, but it warns you. So that's what's going to eventually fix it. The browser manufacturers have taken up the slack where the people setting up websites have just fallen down on the job.
Wasn't Chrome's version that secure message?
No, that padlock has come and gone on many browsers, and it turned out to be a pretty bad idea because 99% of users don't know what it means. And the bad guys figured out how to put padlocks on the page anyway. So it turned out not to do much good. Yeah. Anyway, so let's play with this stuff. Let's set up a buffer overflow. Let me bring up my Kali Linux. It'll be fine. And so here, I made these. All right, so I made hello just before class. I finally fixed a problem in this project right before class. All right, so here's a simple C program. So all this does is import standard IO libraries, so I can use scanf and printf, print a prompt, what is your name, spelled wrong, then read your name, then print out hello your name. So you compile that, with gcc hello.c, put the output in hello, and then when you run it, and you say your name is Sam, it says, hi Sam. That's the intention of this program. The problem is, if you run it and put in a name like this, it crashes with segmentation faults. Because if you look at the source code, I specified 10 bytes of storage for the name, but I didn't limit how much I read. So when I read in 20 or 30 bytes, it just puts 20 or 30 bytes starting at the first byte, going right past the end of the limit without doing anything because this is C. If this was Visual Basic, it would never do that. If it was Python, it would never do that. If you find room for 10 spaces, then you try to put in 30, it will go allocate more space and then put in the 30. But C will never do that to be efficient. It assumes that you must have a plan, never argues with you. So the result is you overrun the memory space available for storing variables, and you get all the way up to the memory space used to store where you left off in the calling routine. And when it tries to go home, the data that says where to go back to is corrupt, and it jumps someplace random and crashes. That's a buffer overflow. And the whole point of exploit development, which we have a class in, is how to improve this. This is a denial of service attack now. I can put in some input that causes the service to crash. And that's fine, but what's cooler is a remote execution exploit. So instead of just putting in a bunch of ones, you carefully put in chosen bytes that don't just cause execution to jump to a random place and crash, they cause it to jump to code I injected and give you control of the machine, which is pretty awesome, and it's a good, clean fun. So anyway, that's a buffer overflow. So we want to patch the buffer overflow. Hello 3 does that. And if you did the project, there's a warning there that you sometimes didn't work because I finally figured out what I was doing wrong. I define my name to have 9 characters, 10 spaces, and I have to read only 9 characters. This is I made this mistake in one version of the project. It was up until this morning. I would read 10 characters after reserving 10, and you can't do that in C. Because if you have a 10-character long string, it takes 11 bytes to store it, because C terminates strings with a null. So if you have 10 characters, you need 11 bytes to store it. So if you reserve 10 characters, you can only have a name up to 9 characters long. Otherwise, you don't have a place to put the null byte, and that causes the string to have extra parts that you didn't put there, which lead to unpredictable behavior. So this one here, the only thing changed here really is that %9 in front of the S, so it's only going to read the first 9 bytes of whatever I type in, and the rest it's going to ignore. So if I compile that one, and get the source code of hello 3, and then run that one. If I put in a short name, it works fine, and if I put in a long name, it works fine. Doesn't crash, nothing bad happens. It just takes the first 9 characters and ignores the rest. This is what you should do, and this is how you protect it, and this is what your security people do, is try all these things, find the problems, and put in all these tests. And in C, it is your responsibility to think of everything and test for everything. It has no automatic defenses at all. Other higher level languages, much less efficient languages like Python and Visual Basic, have a bunch of automatic defenses that will fix these problems, but that means the code is bigger and slower, and you aren't in perfect control of everything it does. Yeah.
I'm not sure if this would apply, but what about for different languages? I know there's like an exploit where like if you put in Chinese characters, an English only thing, it just crashes everything. It happens for the iPhone where like you get a text message and then it just shuts down your phone.
Well, I don't know that particular exploit you're talking about on the iPhone, but I do know in general, character encoding can lead to a variety of entertaining exploits. So especially if you can put in characters in a foreign language, there's a whole series of vulnerabilities that come about from that. Because what happens, the main reason you have bugs is the programmer made some assumption, and that assumption is not true. So for example, when I reserve 10 bytes and I take 9 characters from input, I'm assuming each character is only 1 byte long. But if it's Chinese, each character is 2 bytes long. So I'll overrun. And there are much more subtle ones that happen too. So this is actually the root of a whole large category of vulnerabilities is you write code to be running in one context, and then it goes out of that context and runs somewhere else. And I think I probably should talk about this one. It's coming up in a later class, but we've got to the right point here. This is a good one to understand, and it's right on target here. Let me just get a plain text editor here. Okay, this is something that Moxie Marlinspike found and Dan Kaminsky found, and they both presented it at DEF CON and Black Hat about 6 years ago, and it was bloody awesome. And it goes like this. If you buy an HTTPS certificate, you go to somebody like VeriSign, and you give them money, and they sell your certificate. Okay, in order to buy the certificate, you go to a web form. And you fill in your credit card number and your domain name and your name and address and all that jazz, and you hit buy. That code running on that server was written in Pascal, an almost extinct language, but the code was written decades ago and never looked at again because it worked. Now in Pascal, so let's suppose I have a domain name called evil.com. Okay, in Pascal, the way that is stored, you store the number of bytes, that's 8 bytes long, so you put an 8 here, then you store each byte 1 by 1 as ASCII. So it takes 9 bytes to store, and that's what it looks like. The first byte stores how long the string is. So when you put in evil.com and buy it at a domain, that's how it is stored on their server. But your browser is written in C. And in C, a domain name like evil.com is stored like this. And then you have a 00 byte, a null byte to terminate it. So suppose I do this. I buy this domain name, star, and then a byte of zeros, and then evil.com. If I go to the website and buy that domain name, it will sell it to me with no problem because as far as Pascal is concerned, that's a perfectly fine string. The first byte is star, the next byte is 0, then comes evil.com. It will just put the number of bytes in front, like 10 or 11, whatever it is, and store it in their database and sell me, and I will have that certificate. So now, if I buy that certificate, I now own that domain, star evil.com, star null evil.com. So if I put up a website and I tell you that website is, say, paypal.com, your browser is written in C. So when you go to a website, it's going to download the certificate, and it's going to do 3 tests. Is the certificate from a trusted authority? Well, yes, it is. I bought it from somebody like VeriSign. Is it within the valid date range? Yes, it is. I bought it at the right time. I paid for it. Then that is going to compare the domain names. It's going to ask, does paypal.com equal star 00.evil.com? And because the null byte is interpreted as a terminator, that equals star, which is the wildcard. So if you buy a certificate like that, you can sign any domain in the world and your HTTPS connection will be accepted by the browser. And there were about 14 of those sold before anybody noticed. And Dan Kaminsky had some, and Mark Jamarlin had some, and they demonstrated they could totally defeat HTTPS anywhere with these things. And it was not a bug. The Pascal code was running as intended and the C code was running as intended, but because they were different, when the 2 languages met, you had a huge misunderstanding. It's very much like, I'm talking English and the other person's talking German, and somehow we misunderstand each other seriously, even though we have a translator. So this is what tends to happen. And this is the worst kind of bug. It's a logic flaw. It's not that anybody made a mistake. The Pascal programmers did things right and the C programmers did things right, but nobody was looking at the big picture, putting it all together. And that's the job of the security engineer, to be thinking about those things and catching them. So that's the buffer overflow. Now here's how you take over a machine with a buffer overflow. Instead of just putting in a lot of 1s, which will make it crash, you see you have a name that has room to store 20 variables, 20 characters, but you're able to put in more because the programmer forgot to check for that. So you put in any kind of junk until you reach the end of the storage area for the registers and other variables used in that subroutine, and you hit the area at the end here that controls the return value. There's one place there where the extended instruction pointer is stored. That is the address of the instruction it's going to go to when it returns, that upward jump. So I take that and I write in this number, 700,200. I put in all kinds of junk here, and down here I put my attack. The attack is the egg, and the nops are just instructions that do nothing. There's a variety of instructions you can do that do nothing. One, the simplest one is does exactly not, but there's others. So all I do is create a nop sled followed by my egg, which is what I want. I make it so that the address I put in hits the nop sled. So now when it tries to return from the subroutine, instead of going back to main, it goes here and runs my egg, and now I own the box. This is how buffer overflows work. And so I'm able to inject junk. So in order for it to work, I have to be able to inject code, I have to be able to run that code, and I have to be able to figure out where that code is so I know what number to put there. Those are the conditions. And the way you protect yourself from this is by breaking those conditions. So here's some defenses. Address space layout randomization is a defense Microsoft brought out with Vista. In the old days, you would just start your machine like MS-DOS or Windows 95, and Windows would use the first bit of RAM. And then if you start Microsoft Office, it would use the next bit of RAM, and your antivirus would use the next bit of RAM, and it would just pile them up. It would always use the next available block of RAM. And that meant I could very easily figure out where I am. All I have to do is look at your server, figure out what you're running, make a server like that, and see where I am. And I can pretty much guess where I am. So they had to put in randomization. So each time you reboot the machine, it randomly picks RAM. That's what it is with no ASLR. Just in order, here it is with ASLR. every time you reboot it, it'll put us in a different space. So now, if there's a vulnerability and I can inject code, it's hard to find. I have no idea where I am. I can't find that address. But yeah, it moves it every time. So I don't know what number to put in to get my egg. Address space layout randomization. Good. And next one is data execution prevention. This put permissions on RAM. One of the big problems with RAM is nobody owns it. There's no file name. There's no timestamp, which makes RAM almost useless for criminal forensics. If you find something in RAM, you have no idea who put it there or when it got there. But it also means there was no execution permission on RAM. But about 10 years ago, the people that make motherboards implemented something called the NX bit. So you can mark regions of memory non-executable. And that's what you do. So now the stack, which is where you store these variables and addresses and stuff that are used to return from subroutines, is declared non-executable. So even if the programmer forgets to check and lets you put 1,000 bytes in the password field or something, you can put in this code, but when you jump to it, it won't run because it's non-executable. It will just stop right there with an error message. So therefore, this stops a whole category of buffer overflow exploits. You can inject code, but it won't run because you don't have permission to run. And another defense is a canary value. This is where you put a canary value at the end of the stack frame. So all the temporary storage for one routine is there. Then you have the return value. Then you have a canary here so that if somebody is overriding the stack, trying to hit the extended instruction pointer, they're going to change the canary. So when you try to return from a subroutine, you don't just load the address and go to it. You load the canary and make sure it's not changed. And only if it's not changed, then you load the EIP and go there. Otherwise, you print out an error message. And the error message is stack smashing detected. And modern operating systems have all these defenses. So it is much harder to do buffer overflows. There's always an attack that defeats every defense. So nothing's ever perfect. But this held back the legal hackers for a year. When they first brought out Vista, they went to CanSec West, where people compete to hack the latest operating system, and nobody could take it over at all. All the techniques no longer worked in Vista. And it took a whole year before they upped their game to be able to penetrate these defenses. I might as well mention some of the how to defeat them since we're here. The way you defeat this one, there's two very simple techniques. One is, there's actually three techniques. The first thing is, whenever Microsoft implements a defense, the brochure advertising it is a whole lot more impressive than the actual product they put out. They always only do things about halfway. So in the first case, they didn't actually turn on ASLR for all the routines. Some of the routines are coded without position-independent executables, so they don't have this feature. So all you have to do is find a bug in one of those routines, and this does nothing. The second thing is, they didn't use a big enough random number. They only used like 8 or 12 bits of entropy, so there really aren't a lot of places it can go. There's really only about 1,000 places it could go. So all you have to do is run your attack 2,000 times. You'll get lucky by chance. It'll be where you expect it to be. And the third one is the heap spray. You run a JavaScript exploit where you just make multiple copies of your malware until you fill up all of RAM with it. And then you jump at random and you're likely to hit one. So you don't need to know where you're putting it. You just make many, 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 many copies until RAM is full of your attack. Data execution prevention, this one's kind of easy too. All you have to do is jump to the Microsoft system routine that turns it off. There had to be a way for the programmer to turn it on. There's a way for the programmer to turn it off. There is a routine you can call that will turn off DEP. So you just have to run that first. That's called return to libc. Instead of jumping to the code you injected, you jump to a library code that will do what you want, like turn off DEP. Then you jump to the code you injected. And to defeat the canary value, you have to somehow find a way to read it and put it back in its unaltered state before running your code, or predict it if it's not random enough. And sometimes those things are possible and sometimes they aren't. All these defenses, all any defense ever does is make it more difficult. There's no perfection. So you build a bigger wall, the crooks build bigger ladders. Cops get bigger guns, the crooks get bigger guns. You know, that's all you're ever gonna have is you improve your defenses so the weaker attackers can't get in. The stronger attackers will always find some way to get through whatever defense you have. All right. So that's the programming part. Then there's HTML, of course, is worth knowing about. HTML is just used to bake web pages. And so you just make a plain text file with these formats. Less than and greater than signs are used to indicate control code, so the header tags make print big and paragraph skips a line and break skips a line differently, and on you go. You make source code and it comes out looking pretty after that, and this is glorious HTML, which as itself would be pretty harmless. The problem is browsers mix many languages together on both the server and the client side, and they mix many languages in the same file at the same time. So your HTML actually includes PHP and JavaScript and other languages in the same source code, and that is just asking for more of these translation problems, where you don't even know what language the file is in. It's guessing line by line what language it's in, and if you can trick it into making the wrong guess, it'll misunderstand it. Yeah.
You mentioned that Apple has really good security.
Yeah.
Does Safari, their web app, use HTML, and is it exploitable using the same methods?
That's a very good question. Whether Apple is not more secure because of the quality of their operating system, although it is good. The thing that makes Apple more secure is for the Mac OS, the thing that makes them more secure is they are not being attacked as much. I think that's been proven because now there's viruses on the Mac. They just have been a smaller target, so people haven't focused on them. That's what they said, and I think that was proven when they finally got the Mac viruses. There's now about 100 known Mac viruses, 100 million Windows viruses, and 0 iPhone viruses. The iPhone is essentially perfect not because the code is perfect. There are bugs, but because you cannot run code on it. The only way to get code to run on it is to get it from the Apple Store, and they protect that with humans, not with technology. Humans inspect the apps, and when they get complaints about an app, they figure it out, and when it's bad, they kick the developer out of the program so you can never make any more money. And they won't let you put anything in without paying a fee with a credit card, so they know who you really are, so you can't just make another account and come back. And that punishment is enough to really make people not put malware in the App Store. So if you take your iPhone and you just put in apps from the App Store, they're clean. And they took all the extensions out of the browser. The browser itself is not too dangerous. What's dangerous is Flash and Java and things like that, and they just took them all out. You can't run any of them on your iPhone. So in fact, it is possible to take over an iPhone through the browser, but those vulnerabilities are very rare, and now they're worth $1 million if you find one. There was an offer about 2 years ago. They'll pay $1 million if you have a way to take over a newest iPhone through the browser, because that was how the original Jailbreak Me worked. And as soon as those come out, Apple patches them very vigorously. So, I mean, they try real hard to maintain the security of it, but it's not any more perfect than other code. They have added administrative controls around it. That's what really protects you. But it's a good question. Apple's not intrinsically stronger. For a while, people thought it was, but Microsoft improved their product, and Apple made theirs worse and more popular until they finally got viruses. The way they finally got viruses is they blocked a PDF reader update for 6 weeks, which Microsoft would never have done. But Apple didn't even have a regular update process or anything, or any kind of malware cleaner. They were in the innocent age of pretending there was no problem, and they finally got hosed. And they used to have like 5 reasons to buy a Mac, and one of them was no viruses. And that week, that bullet point went away. And for like a period of a month, they actually sent a letter that leaked to their tech support people saying, if someone calls for help saying they have a virus, tell them you can't possibly have the virus. It's impossible. There are no viruses, and hang up on them. Do not admit that we have a virus, because we're hoping to still pretend it didn't happen. They tried that for about a month. And then that letter leaked out, and everybody screamed, and they finally had to admit, yeah, there's viruses on the Mac. And now there's actually an Apple malicious software removal tool that comes down like the Microsoft one from Apple with your updates to clean off the known viruses. And they have to admit it's not like night and day, Mac and PC. It's not 0 viruses. It's many fewer viruses. But now there's antivirus for the Mac, and you might even want to have it. Anyway, so Perl was designed to handle text input and parse it very easily. Larry Wall wrote it for this purpose, intended for Unix. It's a very strange language. You can just print things with a quote there. That's kind of normal. And the comments use a pound. You can run it in interpreted mode, where you just execute commands immediately on typing them. You very rarely compile it. It's got all the usual stuff, characters and strings and various kinds of numbers. And it's got sub in front of function names. All variables start with $. Comments start with pounds, and the ampersand character calls a function. So it all looks mighty screwy. So here's a subroutine called speak. You define a word with $, then you call it with ampersand. Just makes the word equals hack and calls speak, and the word equals or and calls speak. Looks kind of nuts to me, but I guess you can get used to it. Just a syntax like any other. And so you can make a for loop, which looks very much like a C for loop in Perl. The only big difference is you have these dollar signs in it. And you can then test conditions if IQ greater than 7, same thing. It looks very much like C in that regard, but not quite the same. Anyway, then there's object-oriented programming, which is the next generation beyond these structured languages I've talked about. The structured languages have these subroutines and declaration of variables. The object-oriented take it another level up in abstraction. And this is all the modern ones, C++, Java, Object COBOL, C#. And Forth, I'm sure. I don't know much about Forth, but it's a new Apple language. I'm sure it's object-oriented. They all are these days. So you can now define a class of a data structure that includes attributes that are data and methods, which are functions, all attached to one object. You can define an object in terms of other objects so it inherits properties. And this turns out to be a way to more closely model the real world. So you have classes, and you have a way to separate a member function. So you have an object called employee, and that object has a whole series of attributes like an age, an address, and a social security number. And then it has methods like pay the employee, print a W-2, fire the employee, change the employee's name, promote the employee, demote the employee. There are various things that can happen to an employee, and they're all attached to this one object, which is now a whole cluster of data and code, all attached to the same object. So if I want to do something like get the information about an employee, I'll have to call the employee object and the get employee method of the object. So you have a special character to indicate inheritance. Sometimes it's a dot, sometimes it's a colon, to indicate that you're referring to a specific part of the get employee object. So here's a C++ class. This employee has first name, last name, place of birth, and then they have a method called get employee, and then they have other methods that do things to this employee. And every object has to have a creator that creates it from nothing when you declare a new one, and a destructor that gets rid of it when you're done using it. So you can do the same thing in Ruby. Metasploit was written in Ruby. I think it might have been rewritten, but I think the current version is currently written in Ruby. Ruby is a Japanese language. It's very beautiful and logical. And as you can see, it looks pretty much like C or Java or anything else. Not really all that hard, but it's defining objects and sub-objects with all this indentation. And then there's lol code. There is a whole category of esoteric languages where people just write their own programming language for fun. So lol code was based on lolcatch. So this is how you make a loop. I has a var, I'm in your loop, Yeah, the end of a loop is k thanks bye, and on you go. That's lol code. And then, so here you can go to an online website, you can learn how to write lol code, and you can translate things into lol code. And then there's BrainFuck, which was designed to be the exact opposite of a high-level language. It was designed to be as difficult to read as possible. So the idea is, how baffling could you make a language? And here's how to do it. You may not have heard the Turing machine is where programs started. It was a thing that never even existed. It was this idea. You'd have this thing like a stapler and this long line of tape. They would all have ones or zeros, and you would just do something to the one bit underneath you, and then you move to the right or left, and do something to this bit, and move to the right or left, and so you'd wander back and forth, and eventually answers would appear on that tape. This was a crazy kind of computer. Nobody ever really built one, but it was the first computer in the mind of Turing, and he performed mathematical proof on it. So BrainFuck works on a Turing machine. So the only commands are step 1 to the right, step 1 to the left, add the number under the tape, subtract 1, output the byte, and so on. So there are 8 commands, and they're all punctuation marks. So that is hello world. It will add 1 to this character until it's an H, then move to the right and add 1 to this till it's an E, and so on. This will spell out hello world. That is how baffling BrainFuck looks. And there's something even more horrible called JazzFuck, for JavaScript fuck, where it's all punctuation marks. Nothing but curly braces, square braces, parentheses, and exclamation points, and that is valid JavaScript. And I did a CTF a while ago where there was you would solve one part of the puzzle, and you would now get 67,000 characters of JazzFuck, which was broken, so you had to figure out how to fix it. And once you had fixed it, it would spell out a flag that was like 20 characters long. It took 67,000 characters of code to make one flag. And it took me like days to do that. It was really pretty interesting puzzle. Anyway, this is the thing. It's all just logic, and you could do it in any baffling way you want. And if you start doing like assembly code is about this crazy. because it's just in terms of the real voltages in the chip. And, you know, programmers are sort of nuts, and they enjoy showing off how smart they are by inventing these crazy things. Nobody in their right mind would use those languages to make a real application, but it kind of helps people want to understand, you know, the basic principles of the logic of programming. So let's try some more Kahoots.
For one of my finals, I turned in esoteric language based off of Shakespearean sonnets.
Oh yeah, Shakespeare, I've seen that. There was a CTF where everything had to be in the Shakespearean language, and I was no good at solving that one. Everything is like quotes from Shakespeare.
You have to introduce the variables like stage introduction. So instead of like
enter Romeo.
Exactly.
And then Romeo says something, that's a print statement, and Romeo gives something to Joe's, that's like an addition or something, and it somehow you can figure out what's going on with this stuff.
It was the toughest final I've ever had.
Yeah, oh yeah, I bet. But of course, that way you'll really learn, you know, how to program.
I don't think any programmer knows how to do examiner, which is what you have to code.
That's right. That's right.
There's got to be some English majors who are killing that.
That's right. That was the idea. Yeah. The thing was, when I did it, the compilers and interpreters didn't work. We were supposed to be able to use them, but the ones we could get didn't work on my system. So I would be down to actually trying to. They had like a whole Shakespearean play. You'd have to like run it and get the output, and I couldn't run it in anything I could get working. Yeah. Yeah. It's the same thing, you know. In principle, all you need is some kind of branching, looping, and testing, and you can do anything. All right. Anyway. All right, I'll wait another 5 seconds. There's still people coming. I'll wait a bit. Oh, good. Brain F. That's good. You can tell they're listening. All right, so I'll wait another 5 seconds now. All right. There we go. 5 questions. Which one of these does not prevent buffer overflows? Okay, in GCC, just compiles code. The rest of those are all defenses. All right. Which one allows code injection but prevents its execution? Okay, pretty flat there, but that's data execution prevention. That's what implemented the NX bit. So even if you inject code, it won't run because you don't have execute permissions. All right, and you'll get to know these and love them if you take the exploit development class, man. You'll learn how to fight each one of these. Okay. All right, which one allows code injection but makes it difficult to find? Yeah, that's ASLR, randomizes where things are, so you don't know where you're putting your code. All right, which one detects stack smashing? That's the canary value. When you overrun the stack, you change the canary and it detects that. All right. What language looks like that? Yep, that's the common abbreviation for people who are reluctant to recite the name entirely. So, all right. So, hum, and Rick, and Chad, Born. I might be able to figure out who Chad and Rick, Born and Rick are, but I don't think I'll figure out hum unless they tell me. Anyway, so I think that's it. I'm going to let share go for another minute to see if these people want to send me text through this thing to tell me who they are. Is anybody here? These winners, Rick and Chad Born? Perhaps they're all online. Aha, here comes some names. Good. So, Ricky. Okay, I see who Rick is.
Okay.
And David. Oh, hum. Okay, hum is right. I got hum. Okay, good. And I got Chad Bourne. Good. Okay, thank you, folks. All of you have been identified. So I'm going to stop the share and go to the lab. Farewell.